Dear colleagues, distinguished members of the CHE Awards Committee, and fellow scientists around the world, my name is Professor ABDELKRIM ABOURRICHE from the Laboratory of Materials, Process, Environment, and Quality at the National School of Applied Sciences of Safi, University of Cadi, Ayyad, Morocco. It is with great honor and sincere gratitude that I address you today in the context of the International Chemical Scientist Awards. Today, I will present our work on the development of an eco-friendly composite adsorbent based on clay, chitosan, and sodium alginate shaped into hydrogel beads for the removal of methylene blue from wastewater. We conducted both batch and fixed bed column studies, supported by theoretical modeling using density functional theory. Here is the outline of our presentation. We will first address the problem statement and methodology, why dye pollution is a major environmental issue, and how we designed our approach. We will then present the results of methylene blue removal using clay CZALG beads, covering material characterization, batch and column studies, and DFT theoretical modeling. We will close with a general conclusion and the perspectives of our work. We now enter the first part of our presentation, the problem statement and methodologies. This section lays the scientific foundations of our work and justifies the choices we made regarding materials and experimental approaches. Industrial dye effluents remain a major source of aquatic contamination. Textile effluents in particular contain synthetic dyes that resist biodegradation and exhibit high chemical stability. Even at low concentrations, they reduce light penetration in aquatic ecosystems and interfere with photosynthesis, thereby disturbing ecological balance. Methylene blue, chosen as our model contaminant, is a cationic thiazine dye widely used in the textile, medical, and biological industries. Its presence in water has been associated with oxidative stress in aquatic organisms and adverse human health effects upon prolonged exposure. This underscores the urgent need for efficient and sustainable treatment technologies. Among the available water treatment strategies, adsorption is widely regarded as one of the most effective and economically viable techniques. It is a surface phenomenon by which molecules from a fluid, here methylene blue, bind to the surface of a solid called the adsorbent at active sites. The adsorbate migrates from the solution toward the adsorbent surface where it becomes immobilized. This process is valued for its operational simplicity and high removal efficiency, making it highly suitable for both laboratory and industrial scale applications. There are two main types of adsorption. Physical adsorption or physisorption involves weak van der Waals forces and is reversible. Chemical adsorption or chemisorption involves stronger covalent or ionic bonds. Among commonly used adsorbent materials, we find activated carbon, highly effective but costly, zeolites, natural clays, and polymers. Natural clays are particularly attractive due to their layered structure, high surface area, and cation exchange capacity. However, their adsorption efficiency is often limited by structural heterogeneity and restricted functional group accessibility. This is precisely why we chose to modify them with biopolymers to overcome these limitations. Our strategy consists of combining three natural and eco-friendly components: natural clay collected from a mining site near Safi, chitosan obtained by deacetylation of chitin extracted from crab shell waste, and sodium alginate, a marine-derived polysaccharide. The synthesis proceeds in three steps. First, chitosan extraction from crustacean shells via demineralization with HCl and deproteinization with NaOH. Second, preparation of the clay C's composite by mixing 70% clay and 30% chitosan and stirring for 48 hours. Third, fabrication of clay CZALG hydrogel beads by ionotropic gelation. The suspension is extruded dropwise through a syringe into a 4% CaCl2 solution, where instant bead formation occurs through ionic cross-linking between calcium ions and alginate chains. We now move to the second part of our presentation, dedicated to the experimental and theoretical results of methylene blue removal by clay CZALG beads. This section covers characterization, batch adsorption studies, fixed bed column experiments, and DFT theoretical analysis. Structural characterization by FTAR and XRD confirms the successful integration of the three components into a unified hybrid network. The F-tier spectrum of Clay-Xi ALG simultaneously displays the characteristic bands of chitosan, OH and H stretching near 3D279 cm1, clay, Psi-OC, and Al-OSI stretching bands, and alginate, COO, and COC bands. These bands are slightly shifted or broadened, reflecting hydrogen bonding, Ca2 plus alginate cross-linking, and polymer clay interactions. After methylene blue adsorption, noticeable changes in the NH2, OH, KOO, and Psi-OSI bands confirm the direct involvement of these functional groups in dye binding. The XRD patterns show that the crystalline structure of the clay phase is preserved within the composite, with a crystallite size estimated at 32 nms using the Scherer equation. Thermogravimetric analysis shows that the Clay-Xi ALG composite displays intermediate thermal behavior between the organic components, chitosan and alginate, which degrade between 200 and 330 degC, and clay, which remains stable up to 900 degC. Notably, the beads exhibit a shift of the main decomposition zone to higher temperatures and a reduced total mass loss, indicating increased thermal resistance arising from polymer clay interactions, Ca2 plus alginate cross-linking, and hydrogen bonding. Regarding zeta potential, the point of zero charge of the composite is determined at pH 6.2. Below this pH, the surface is positively charged. Above it, the surface becomes negative. Scanning electron microscopy reveals that the beads exhibit a globally spherical geometry with a relatively uniform external surface, confirming the effectiveness of ionotropic gelation. At higher magnification, the surface is rough and heterogeneous, characterized by lamellar aggregates and interconnected microcavities arising from the homogeneous dispersion of clay platelets within the chitosan alginate network. This hierarchical architecture enhances the effective surface area and improves the accessibility of functional groups NH2, OH, and COO, thereby promoting dye binding. After methylene blue adsorption, the surface becomes more compact with evident pore filling, indicating strong adsorbate-adsorbent interactions. EDX analysis confirms the appearance of Cl and an increase in nitrogen intensity after adsorption, providing direct evidence of dye immobilization within the composite. We investigated the influence of the Clay-Xi composite proportion in the alginate beads. Results show that the 1-2 mass ratio 2G of Clay-Xi per 1 grain of alginate provides the highest adsorption performance, approximately 98%, markedly superior to the 1-1 and 1-3 formulations. This optimal ratio reflects an appropriate balance between the inorganic and organic phases within the alginate network, maximizing the density of accessible functional groups and preserving a well-structured porous architecture favorable to dye diffusion. Furthermore, comparing clay alg beads without chitosan versus Clay-Xi alg clearly demonstrates the crucial contribution of chitosan. Removal efficiency increases from about 52% to 98%, thanks to the abundant amino and hydroxyl groups that strengthen electrostatic interactions with the cationic dye. For all initial concentrations tested, 50, 100, and 200 mg/L, the removal rate increases rapidly during the first 120 minutes, reflecting the high availability of active sites and a strong mass transfer driving force. The curves then gradually reach a plateau, indicating equilibrium. While increasing the initial concentration reduces the percentage removal due to progressive saturation of available sites, it simultaneously leads to a significant enhancement of the equilibrium adsorption capacity key, which increases from approximately 120 mJ at 50 mJ up to nearly 270 mJ at 200 mJ. This is attributed to the higher concentration driving force intensifying the diffusion of methylene blue molecules from the bulk solution toward the internal pores of the hydrogel beads. This behavior is typical of systems dominated by chemisorption and strong electrostatic attractions. The composite exhibits high removal performance across a wide pH range from 2 to 8, with a maximum efficiency of 98.34% achieved at pH 6. This optimal behavior is attributed to the combined effect of the bead's porous architecture, which enhances molecular diffusion, and the high availability of active functional groups NH3 plus, NH2, OH, COO, and siloxane sites capable of interacting with the cationic dye. Near neutral pH promotes particularly favorable electrostatic attraction between methylene blue and the partially protonated amino and hydroxyl groups of ketosane. In contrast, at strongly alkaline conditions, pH 10, a significant decrease to 55.8% removal is observed, mainly due to the deprotonation of surface functional groups, which generates an increased negative surface charge and consequently enhances electrostatic repulsion toward the cationic methylene blue molecules. A clear decreasing trend is observed as temperature increases from 15 to 45 degrees C. The highest removal efficiency, approximately 98%, and adsorption capacity, around 120 milliliters G, were obtained at 15 degrees C, after which both parameters progressively declined. This behavior confirms the predominantly exothermic nature of methylene blue adsorption onto clay-siege algae. Increasing thermal energy enhances the mobility of dye molecules in solution, but simultaneously reduces their residence time at the adsorbent surface, limiting the formation of stable electrostatic and hydrogen bond interactions. Additionally, elevated temperatures may cause partial structural relaxation or swelling of the hydrogel matrix, reducing the accessibility of internal adsorption domains. These findings underscore the suitability of clay-siege algae beads for wastewater treatment at ambient or mildly cool temperatures. The thermodynamic analysis carried out between 288 and 318 K provides several key insights. The distribution coefficient Kd decreases progressively with increasing temperature, confirming that adsorption becomes less favorable at higher temperatures. The negative Gibbs free energy values dGdG ranging from 6.57 to 14.36 kJ/mol confirm that the process is spontaneous throughout the studied temperature range. The enthalpy change dHdEg equals 19.95 kJ/mol, confirming the exothermic nature and placing the process within the typical range of physical adsorption between 5 and 40 kJ/mol. Finally, the negative entropy change dsdG of 20.8 J-mol/K indicates a decrease in randomness at the solid-liquid interface during adsorption, with methylene blue molecules becoming more ordered and spatially constrained upon attachment to the active sites of the hydrogel surface. The equilibrium data were analyzed using Langmuir, Freundlich, and Temkin models. The Temkin model provides the most accurate description, supported by the highest correlation coefficient R2, Bries 0.99, and the lowest error values RMSE, Bries 5.2, and A2, Bries 0.6. This indicates that adsorption is governed by adsorbent-adsorbate interactions on an energetically heterogeneous surface, with a linear decrease in the heat of adsorption with increasing surface coverage. The high Temkin equilibrium constant Kt of 2.2 x 103 Lg demonstrates strong binding affinity between methylene blue and the composite surface. Although the Langmuir model yields a high theoretical maximum capacity of 303.03 mg and a favorable separation factor RL of 0.115, its larger error values confirm that adsorption does not occur on a perfectly homogeneous surface. The Freundlich parameter 1n 0.18 also confirms favorable adsorption and surface heterogeneity. The fixed bed column study evaluated the influence of three operating parameters. First, bed height, increasing it from 10 to 20 centimeters raises the breakthrough time from 20.5 to 102.8 minutes, and the exhaustion time from 280 to 500 minutes. A taller column provides more active sites and a more extended mass transfer zone. Second, initial concentration. Increasing C0 from 50 to 200 min-hours meter L sharply reduces breakthrough time from 102.8 to 20.09 minutes, as the higher mass transfer driving force causes faster site occupancy. Third, flow rate. Increasing Q from 1 to 3 ml min shortens breakthrough time from 102.8 to 18.05 minutes. To understand molecular level interactions, we perform DFT calculations at the B3LYP631GD level. Methylene blue presents a small HOMO-LUMO energy gap of 1.15 eV, reflecting high electronic mobility and strong chemical reactivity, which facilitates its interactions with electron-rich adsorption sites. Chitosan has a very large gap of 16.28 eV, indicating high intrinsic stability, while alginate shows a moderate gap of 4.59 eV due to its negatively charged carboxylate groups. Upon complex formation, the energy gap of the AlGMB complex is reduced to 1.58 eV, indicating strong electronic coupling between methylene blue and the alginate adsorption sites. The electrophilicity index of the AlGMB complex is significantly higher than that of the ChemB complex, confirming that alginate provides more favorable electronic conditions for dye adsorption, consistent with the experimental observations. The adsorption of methylene blue onto Clay-CZAlG beads is governed by a cooperative mechanism combining several interaction types. Electrostatic interactions constitute the primary driving force. Above the point of zero charge pH 6.2, the negatively charged surface strongly attracts cationic methylene blue molecules. Hydrogen bonding occurs between the polar functional groups of the composite, OH, NH2, and COO, and the nitrogen and sulfur atoms of the dye. pp stacking interactions take place between the aromatic rings of methylene blue and the glucosamine backbone of chitosan, while NP interactions are possible between the lone electron pairs on oxygen and nitrogen atoms and the p electron system of the thiazine chromophore. This multi-interaction mechanism accounts for the high adsorption capacity and structural stability of the composite material under varying conditions. In conclusion, our work demonstrates that Clay-CCAlG composite hydrogel beads constitute an effective, stable, and sustainable adsorbent for methylene blue removal. First, the beads achieve a maximum adsorption capacity of 303.03 mCarchi at 15 degraags, significantly higher than many comparable systems reported in the literature. Second, the Temkin model best describes the adsorption isotherm, revealing an energetically heterogeneous surface with significant adsorbate-adsorbent interactions. Third, kinetics are well described by the pseudo-first-order model, with intraparticle diffusion contributing without being the sole rate-limiting step. Fourth, thermodynamic analysis confirms a spontaneous and strongly exothermic process. Fifth, the Thomas model successfully predicts fixed bed column performance under dynamic conditions. Finally, the material maintains a removal efficiency above 80% after 5 consecutive regeneration cycles, demonstrating operational stability and reusability. Our research perspectives are structured around 3 main directions. First, we intend to extend the study to anionic dyes from different families, such as Congo Red and Alizarin Red S, in both single and binary systems to better understand competitive adsorption mechanisms. Second, we will evaluate the efficiency of Clay-CCAlG for the removal of heavy metals, particularly PB2 and other organic pollutants present in industrial wastewater. Our preliminary results already show 93% removal efficiency for PB2I, which is very encouraging. Third, we plan to explore adsorbent behavior under real effluent conditions with complex industrial matrices in order to validate its potential for large-scale and continuous flow applications, moving beyond controlled laboratory settings. Here are our main bibliographic references. I would particularly like to highlight our previous works on clay chitosan composites for the removal of both cationic and anionic dyes, published in Chemical Engineering, Science, and Environmental Research in 2024, as well as our recent publication in Materials Chemistry and Physics in 2026. These studies form the experimental and theoretical foundation underpinning the results presented today. The complete list of references is available in the full article published in the International Journal of Biological Macromolecules. Thank you very much for your kind attention.